Okay, so then from Fourier integral formula I can always find Fourier cosine formula. What is Fourier cosine formula? So, notice again, let me write down. So, my Fourier integral formula I denoted by, so my Fourier integral formula. So, I am using some short notation here. So, I denote by the following. So, this is 1 by 2 pi integral from minus infinity to infinity f of zeta e to the power negative I k zeta d zeta. Well, this was with a 1 by square root 2 pi. We see that our this exponential, this is actually a complex number, this is given by cos k zeta plus I sin k zeta, right. Now, well, so that is my Fourier transform. So, where now my function f is 1 by square root 2 pi integral of this Fourier transform f k e to the power I k zeta d k from negative infinity to infinity. So, that is what we have seen. So, let me just combining these two, I am going to derive this Fourier cosine formula here. So, I have f of x is equal to 1 by 2 pi. So, I am just rewriting what I have mentioned earlier, minus infinity to infinity. So, f of zeta I have e to the power negative I k zeta, and then I have e to the power I k zeta. I had two integrals with respect to two variables, one was d zeta, the other was d k, and of course, I had this double integral from minus infinity to infinity. Now, I am going to combine these exponentials, right. So, I have, well, so I need to distinguish between these two here. So, I have this as e to the power negative I k zeta, and I have here as e to the power I k x here. So, this is x. So, let me just combine this. So, I have 1 by 2 pi double integral f of zeta e to the power I k x minus zeta, right, d zeta d k. Okay, as I mentioned that this is nothing but a complex number. So, cos of this argument plus I times sine of this argument, right, from minus infinity to infinity, minus infinity to infinity. Now, notice that if I were to, let me just break it down. So, I have double integral f, one of the integral is cos d zeta d k, the other one is I times double integral f and then sine of the argument d zeta d k. Notice that sine is an odd function. So, when I integrate sine over this variable k d k, when I integrate this sine value, it disappears and this integral is going to give me 0. So, I am only left with the cosine integral. Now, also cosine, the cosine function is an even function. So, I have sine is an odd function, cosine is an even function. So, I can always replace my first integral 1 by 2 pi. So, this is from negative infinity to infinity, and then of course, since this is an even function, I can replace it as 2 times 0 to infinity f of zeta cos k times x minus zeta d k d zeta, right. So, of course, my 2 cancels with 2, and here is my, let me write it down in a way that people can see. So, this becomes 1 by pi integral from 0 to infinity f of zeta cos k x minus zeta d zeta, and I am going to take this variable dk out. So, why I have done that is because notice that this is my Fourier cosine formula. Okay. So, I have used it to derive this. I have used the fact that cosine is an even function. So, similarly, I have the so called Fourier sine formula. Fourier sine formula, which I denote it as, well, let me just denote my sine formula. I am going to distinguish between the sine as f of s of k. So, s denotes sine, and if I have c, it is cosine. So, f s of k is 1 by pi integral from 0 to infinity f of zeta sine of k x minus zeta d zeta. Okay. So, that is the way we define our Fourier cosine and sine formula. Now, of course, if I have, so when to use the Fourier sine formula and when to use the Fourier cosine formula. So, if I have that f is an even function, then the natural choice is to use the Fourier cosine formula, and in that case my f c is 2 by pi integral from 0 to infinity f of zeta cos, well, k zeta d zeta. So, this is the case when I have f of x is f of minus x, when f is even, right. And of course, similarly, if f is odd, I can always use my Fourier sine formula as, notice that the 2 is coming out. Why 2 is coming out? Because of the fact that, well, we have expanded our sine and cosine formula using our summation rule. So, that has brought down this factor here. So, similarly, we have f s given by 2 by pi 0 to infinity f of zeta sine k zeta d zeta. Okay. So, let us now recap a little bit. So, I have introduced the Fourier integral formula. I also call it as the Fourier transform denoted by f t, which is given to be equal to, and of course, for next time for short notation this is given by f of k, or this is also called as the curly f of our argument function f, and the formula is 1 by square root 2 pi integral from minus infinity to infinity e to the power negative I k x f of x dx. Okay. And then of course, we have Fourier cosine formulas, Fourier sine formulas. Most important thing is the Fourier inverse. What is the inverse formula for, or the Fourier inverse transform? The inverse transform I denoted by as this curly f inverse of f equal to 1 by square root 2 pi integral from minus infinity to infinity e to the power I k x f of x dx. So, I just want to recap that whenever we have a problem which is non-periodic, we are going to use Fourier transforms. Whenever we have functions which are non-periodic, but it is defined on a half domain and it is odd, then we are going to use the Fourier sine series. And whenever the function is non-periodic and also the function is even, it is natural to use the Fourier cosine series. So, please remember all these facts when we are going to do some application problems. Now, before I move ahead, I just want to highlight there is another notation which is widely used by people in electrical engineering. So, what is used? So, Fourier transforms are mostly in electrical engineering, Fourier transforms are mostly used in the definition of signals, and in that case my variable x in the Fourier transform is going to be replaced by another variable t. Now, as we will see, of course, in the application t will denote time, but let us keep it general, t is another variable that is replaced by from x, and similarly my variable k in the transformed plane is replaced by omega, which is also 2 pi nu. So, what is this? Omega is sometimes also called the angular frequency, and k in our transformed plane is called as the wave number. So, I am talking about all these concepts because we are going to introduce all these notions when we do some problems. So, let us move ahead. So, here is one quick example to show you how Fourier transforms are used. So, the example tells me find the Fourier transform of e to the power negative a x square. So, it is a very straightforward application of Fourier transform. So, we see that the Fourier transform of this e to the power x square, I denote it as f of k, is given by 1 by square root 2 pi. I am just going to use the formula from negative infinity to infinity e to the power I k x times e to the power negative a x square dx, right. Now, we have to now integrate this integral, which is an infinite integral. So, that becomes the way to do this integral is we are going to complete the squares. So, what do I mean by that? Please note that I can write my the factor on top of this exponential, I can write it as follows. This is a times I plus I k by 2 a whole square. So, and then let me just put a huge bracket here, so that we do not confuse, plus k square by 4 a, and the bracket is over here, and then this is integrated with respect to dx. Now, please check this, that this thing on the top of this exponential is actually the sum of these two expressions. So, then why we have completed the square? Notice that this second term, this term is independent of x. So, I can actually pull out of this expression out of this integral. So, this becomes k square by 4 a divided by square root 2 pi integral from minus infinity to infinity e to the power negative a, and then the first factor remains x plus I k by 2 a square dx. Now, there is a very standard theorem in calculus which tells us that if I have an infinite integral of this factor e to the power a y square dy, this value is equal to square root of pi by a. So, I am going to use this result, it is available quite common in calculus books, and let us use this result to come to the final answer. So, the final answer, please check that the final answer that I get is that the Fourier transform is 1 by square root 2 a e to the power negative k square by 4 a. Okay. So, let me just use a red pen to highlight the answer here. Okay. Okay, so let us do some more examples. So, I have to find the Fourier transform of this function. This is 1 minus absolute value of x by a times h of 1 minus absolute value of x by a, right. Now, what is this function h? The h is called the Heaviside function, right. So, if I have h of x, it is defined as 1 if x is positive and 0 if x is negative. Okay. So, this is a unit, let me call it as a unit Heaviside function, because it gives you either 1 or 0. Okay. So, then my Fourier transform of this function will be, again I use the formula 1 by 2 pi, this time integral of 1 minus mod x by a times the Heaviside function of the argument e to the power I k x dx. Notice that Heaviside function vanishes if the argument is less than 0. It vanishes when the argument is less than 0, which means that my Fourier integral reduces to this finite integral from minus a to a 1 minus mod a by x e to the power negative I k x dx. Why does this vanishes, transforms into this finite integral? Because only in the finite integral this Heaviside function takes the value 1, otherwise this Heaviside function takes the value 0. So, then you see that this function is an even function, because if I replace x by minus x, the value does not change. So, I can always change this integral into a new integral. This is 2 times integral from 0 to a 1 minus x by a e to the power I k x dx. I have used the fact that the function, the earlier function was an even function. So, that has brought in this factor of 2. Okay. So, then you can see that this is, well, what next to be done is the fact that, well, we see that this is also cos of k x plus I times sine of k x, right. So, I could have broken down the integral into 2 integrals. So, one of the integrals would be 1 by 2 by square root 2 pi 0 to a 1 minus x by a cos of the argument, and the other integral would be the sine of the argument, right. Well, it actually makes sense if we see this case here, right. So, if I were to break this integral into the cosine and the sine case, and my second this function is an even function. So, the product of even function with an even function will be an even function, and the product of an even function with an odd function, where sine is an odd function, will be an odd function. So, an odd function over an interval from minus a to a is going to give me 0. So, only this one survives, and this one is equal to 0, right. So, all I am going to get is 2 by square root 2 pi integral from 0 to a 1 minus x by a cos of k x dx, right. So, then what to do next? We are going to use integration by parts. So, I am going to take this as my first function and this as my second function. Okay. So, let me write it down. So, I have the following: 2 by square root 2 pi 0 to 1. I am now going to rewrite this integral as follows. So, this becomes d dx of sine a k x by a k dx, and that brings in an a. What I have done here is I have used a new variable x prime, which is x by a. So, choose my new variable x prime as x by a, and again I replace, since x prime is a dummy variable, I replace x prime by x again, and then we can see that this is nothing but my cosine. This is going to give me my cosine function if I were to differentiate this, right. So, this is nothing but the previous step. So, why did I choose to write it in this form? Notice that this is my first function, this is my second function. So, if I do integration by parts, I am going to easily be able to integrate this. So, after doing all the calculations, so I am leaving all the calculations here. There are some steps which I request the students to see what they are, integration by parts. I come to this new integral, which is integral from 0 to 1 d dx of sine square a k x by 2 divided by a k by 2 whole square, okay, times dx. Now, this is quite easy to integrate because this is already in the derivative form, and I get the answer to be a by square root 2 pi sine square a k by 2 divided by a k by 2 whole square. Okay. So far we have seen some examples of the use of Fourier transforms. So, let me now introduce the Fourier transform. The problem comes how to evaluate Fourier transform of functions in which we have some difficulties, right. So, specifically I am going to introduce Fourier transforms of generalized functions. So, what are these generalized functions? So, Fourier transforms of discontinuous or discrete functions can be found by approximating those functions as sequence of, let me call this generalized function as GF, sequence of generalized functions. So, what happens is that most of the time this discontinuous or discrete functions we cannot evaluate Fourier transforms, right. So, it is better to approximate these continuous or discrete functions into the sequence of the so called generalized functions that I am going to introduce now, and the Fourier transforms of these generalized functions are available, right. So, next I am going to show that if I am able to figure out the Fourier transform of this sequence of generalized functions, I will show that that corresponds to the Fourier transform of the corresponding discrete or discontinuous function, right. Now, so long story short, if I am not able to evaluate the Fourier transform of a certain function, all I need to do is to represent that function into a sequence of so called generalized functions for which Fourier transforms are available, right. Now, I am going to introduce some more notions. One of the other notions that I introduce is the so called good functions. So, what are good functions? So, good functions are those functions which are infinitely differentiable over the real line, I denote it by C infinity r, and it decays sufficiently rapidly such that all its derivatives decays to 0 faster than x to the power minus n, that is for all integers n positive, right, as my variable x goes to infinity, right. Now, to give you the definition in short, good functions are those real or complex valued function, good functions are those real or complex valued functions such that I have this following limit goes to 0. So, limit x tending to minus or plus infinity x to the power n g n of x, that is equal to 0. So, I am taking here I am taking the nth derivative, right. So, the nth derivative decays faster than x to the power minus n, right, for all n and n. Okay. So, then what do I have is that let me just give you some examples of good functions, right. So, one of the examples is, well, this function, let me denote it by this function g x. So, here is one example of a good function which is to be given by e to the power negative 1 minus x square to the power minus 1, if x is between minus 1 and 0 otherwise, right. We see that in this case this is a good function if we use the definition, but it does not have a Taylor series, it does not have a Taylor series expansion around x equals plus minus 1, right. For the other cases it is easy to see the Taylor series exists, but around plus minus 1 we see that in for this good function the Taylor series does not exist. So, what is the conclusion? The conclusion is that good functions need not, well, good functions need not have Taylor series expansion, right. So, that is the slightly against the intuition that we have. Then I must give you an example of functions which are not good functions. So, one of the cases is this one, e to the power minus mod x. Why? Because it is not differentiable, at x equals 0. Another case of not good function is 1 plus x square to the power minus 1. Why? Because it decays too slowly than what the definition tells us as x goes to plus minus infinity. Okay. So, at least we know what are good functions and which functions are not good functions. Okay. So, then one of the properties is if I have a function which is good, a good function, then the function g which is defined as the integral of good function, the integral of good function is also a good function if and only if this integral of this good function exists, right. So, if you can evaluate the integral, this is finite, well, the integral of a good function is also good function, right. Well, another property is good functions are absolutely continuous, absolutely continuous. So, I am not going to go into the definition of what is absolutely continuous, that could be found in regular calculus text. Well, what I want to highlight is it is much stronger than your continuity, or uniform continuity scenario, right. So, it is absolutely continuous here. Okay. Then I want to introduce another function, another definition called